Hey YouTube, and welcome back to It Just Clicked. Today we're going to be talking about angles and triangles. So to start us off with angles, let's talk about lines. So before we had just the one line, like we said in the first dimension, and now that we're in the second dimension, we can have more than one line. In fact, we can have a lot of lines, a whole bunch of lines. But what we're going to talk about is just two lines. In fact, we're going to talk about two different kinds of relationships between two lines. The first relationship is when two lines intersect or cross, but they cross at exactly a 90-degree angle. If you remember from the last video, a 90-degree angle is basically a quarter turn of an entire circle, or we can think of it as like a corner. So if two lines intersect perpendicularly, they will create four corners. The second type of relationship are parallel lines. Parallel lines never intersect, ever. And the only way for that to be possible is if both of them are completely flat in relation to each other and neither of them have been rotated at all, and they are placed a distance away from each other. So what we want to look at are two parallel lines, and then we want to take what is known as a transversal line, which is just a line, but we're going to take it and intersect both of the parallel lines with it. It is called a transversal line only because it intersects two parallel lines. We do this because it can tell us a lot about the relationships between angles. We're going to talk about 5 different relationships that exist between these parallel lines and the transversal line with their angles. The first that we're going to talk about are corresponding angles. Corresponding angles require us to understand what it means for something to have a relative position. Let's say I have two sections of houses. In each section, there are 4 houses, and they're next to each other. We could look at these as two separate sections or as one whole section. If we break it up into two separate sections, then we could say that there's a corresponding house in each section. And what that means is where the house is in one section of 4 is going to correspond to the house that's in the same place, the same relative place in the other section. And we say relative place because obviously it's not in the same exact place, but since both of the sections look the same, then the place feels like it's the same. So we say it's relatively the same place. So we'll use this exact same concept on our parallel lines and our transversal. Because when we look at it, we can think of dividing this up into two sections of 4 angles. So all we have to do is think of it as the houses. Any angle that shares a relative place with another one in another section will be the same angle. So that's corresponding angles. The next one is vertical angles. Vertical angles are two angles that are opposite of each other when you have two lines that intersect. These angles will also always be equal. For the third and fourth, I'm going to kind of group them together because it's alternate interior angles and alternate exterior angles. Like the corresponding angles, with this one we want to kind of group up the angles again into two sections of 4. Except this time we're going to group up the 4 angles that are closest to each other and the 4 angles that are furthest from each other. So now that we've grouped them up into interior angles and exterior angles, we need to remember that these are alternate interior and exterior. So that means going back to the idea of relative place, instead of being in the same relative place, they're going to be in the opposite relative place, the alternate side instead of the same side. So really we could kind of think of this as just diagonal from one another, and these angles will be the same. And the last to talk about are supplementary angles. And supplementary angles are just any angles that end up laying on a flat line. Because like we talked about before when we were talking about rotating halfway through a circle, you end up with a flat line when you have 180 degrees. So anytime you have multiple angles that make up a flat line, they have to add up to 180 degrees. So now that we've covered some of the angles and the relationships between them, let's get on to our first shape, which is going to be a triangle. A triangle is going to be made up of 3 sides, and the interior angles, so if you add up all of the angles inside of a triangle, they will always equal 180 degrees. And we can see why using the information that we just learned. If we draw the simplest version of a triangle, which is an equilateral triangle, which just means that every side is the same length, then we can put 2 parallel lines next to it, one at the top and one at the bottom. And now we basically have 2 transversal lines. If we look at the 3 angles created by our triangle at the top here, we could label these angle 1, angle 2, and angle 3. And if we look down at the bottom, and since we only care about the inside of the triangle, we'll just look at these two angles and we'll call them angle 4 and angle 5. The 5 relationships between angles that we talked about earlier are called theorems, and we're going to use one of those theorems here. It's the alternate interior angles theorem. And what this theorem will tell us is that angles 1 and 4 and angles 3 and 5 are the same angle. We're also going to use the supplementary angles theorem to know that angles 1, 2, and 3 have to add up to 180 degrees. So now if we use our substitution to replace angle 1 with angle 4 and angle 3 with angle 5, we know that angle 2 plus angle 4 plus angle 5 also have to equal 180 degrees. And this proof helps us understand why triangles have an interior angle measure of 180 degrees. So now let's get into the different types of triangles. First, we'll look at the equilateral triangle since we already talked about it. It's going to have angle measures of 60 degrees, 60 degrees, and 60 degrees, and all of the side lengths are going to be equal. So it could be something like 1, 1, 1. It's important to note that the angles are all the same because the side lengths are all the same. Now let's take an equilateral triangle with side lengths 2, 2, and 2, and let's cut it in half and see what happens. There are quite a few things to notice here. The first might be that our angle at the top is now 30 since we cut it in half. The second thing to notice is that when we cut our triangle in half, we created a perpendicular intersection with the base of the triangle. Because this is a perpendicular intersection, we know that this angle will be 90 degrees. A triangle that has a 90-degree angle is known as a right triangle. If you'll notice, there's a side that we didn't touch, that we didn't cut in half or do anything to. So that side still has a length of 2. However, the base of our right triangle was cut in half. So now it only has a length of 1. So we no longer have equal lengths all around on our triangle. But how do we know how long the side is that we use to cut the triangle in half? This is where we'll introduce a really helpful idea that you'll want to use a lot, and it's called Pythagorean theorem. Pythagorean theorem only applies to right triangles, but it helps us to find any given side if we know at least 2 of the sides. The way Pythagorean theorem is set up is a squared plus b squared equals c squared, where c is the diagonal line in your right triangle. It's known as the hypotenuse. The other 2 lines, or sides, in our right triangle are known as the legs, and in the equation a squared plus b squared equals c squared, either leg can be a squared or either leg can be b squared. Just always make sure that you're putting in all of the side lengths that you know. So if we were to set it up for this triangle, we would have a squared plus 1 squared equals 2 squared. 1 squared is 1 and 2 squared is 4, so the question is what number, when we square it, gives us 3? If you remember from our video where we talked about exponents and square roots, you might know that the square root of 3 when squared equals 3. Because remember, whenever you square a number in a radical, it removes the radical. So now we know the last side length is the square root of 3, and this ratio 1, 2, and the square root of 3 always exists for this specific kind of right triangle. In fact, it's called a special right triangle because it has angle measures of 90, 30, and 60. If you forgot, we know the last angle is 60 because that's still a part of the equilateral triangle that we didn't touch, just like the side. Another way to find this last angle, or any last angle, is you can take the 2 angles that you know, add them together, and then subtract that from 180 degrees. Because remember, the interior angles of a triangle always add up to 180 degrees. There's another type of triangle that can also be a right triangle, and that is an isosceles triangle. An isosceles triangle is a triangle that has 2 side lengths that are the same, whereas the third one is different from the other 2. And the ratio for the isosceles triangle is side length of 1, and hypotenuse length of the square root of 2. Because remember Pythagorean theorem, a squared plus b squared equals c squared, and 1 squared is just 1, so it's 1 plus 1 equals 2. But it's the square root, so it's got to be the square root of 2. It's a lot better to understand why these are the ratios they are because of Pythagorean theorem than try to memorize them or something like that. Because these ratios will be helpful when you see triangles like this, but it doesn't have to be a memorization thing, it can be an understanding Pythagorean theorem thing. And the last three types of triangles that we're going to talk about aren't going to have ratios, but they are going to have rules with them. The first is the obtuse triangle. An obtuse triangle is a triangle that has an angle that's larger than 90 degrees. The next is the opposite, which is an acute angle. An acute angle is going to have all angle measures be less than 90 degrees. So an example of an acute angle would be an equilateral triangle because it's 60, 60, 60, which are all less than 90. And the last is a scalene triangle. And a scalene triangle is a triangle that has three different side lengths. So the angles are also going to be different. There are some patterns here that you're really going to want to be aware of as we move forward. The first is all of the angle theorems are really important patterns to be on the lookout for. These will help you in a lot of situations, especially the supplementary angles theorem, because it's really easy to forget that a straight line is just 180 degrees. And the second are what are known as Pythagorean triples. So we talked about the Pythagorean theorem, but just know that there are patterns of triangles, and we call them triples, that exist, which all fit Pythagorean theorem. For example, 3, 4, 5 would be a Pythagorean triple. Another one is 6, 8, 10, and we can check these triples just by doing the math. For example, for 3, 4, 5, 3 squared is 9, 4 squared is 16, and 9 plus 16 is 25, which is 5 squared. And that'll do it for angles and triangles. In our next video, we're going to get back to functions and talking about some of their properties, but we'll visit the topic of angles again, so don't worry. But for now, remember to like, comment, and subscribe, and we'll see you in the next one.